Greetings everyone. Actually, this is a recorded session of the fifth session that we had yesterday on 27th. But due to some reason, the recording option was not available, and I was not able to record the session yesterday. So today, I have been told by the team members that I have to upload the video again, even it's without the students. So this session, it will be dealing with the numerical problems and the concepts that we just learned yesterday in the live session, but I was not able to record that. So this session today is sort of uh, a recording of the same lectures or same concepts and the numericals that we actually yesterday learned between 3 to 5. Uh, so today I'm just going to I might hurry a bit during this because there is no audience, but I will try to just maintain a bit what you can say, um, a bit calmness while solving the problems, so that the people who weren't present in this session are able to catch up with the things. So basically, let's start with this problem that we had solved yesterday first. And this problem states that basically, let me turn off the video itself today because there is no audience. So let us turn off the video itself, and let's solve the problem, which says that we have been given some electron concentration, and this electron concentration, wait a second, let me check first if this session is getting recorded. Yes, because the previous problem was with the recording. So this problem says that this electron concentration varies. This profile here given is like a linear equation. You can say that this linear equation in X has been given for the electron concentration, and this electron concentration has been given to be equal to n at x equal to 0 and 0 at x equal to L. So this is some decreasing electron concentration in X, and we have been told to find the total number of electrons which are present in this material, and we have been given the cross-sectional area for the same. So the let's write down the equation for this electron concentration first. Wait a second. Okay, let's write down the equation first. So wait a second. Okay, so basically the equation for this electron concentration as a function of x will simply be some intercept plus slope times the x coordinate. So we now have that we have two conditions. One is that x, when x is 0, the concentration is n, and when x is L, the concentration is 0. So basically, let's use the first condition. N of 0 is equal to n. It implies a plus b of 0 is 0, or it implies a is equal to n. So this is the first condition. Now for the second condition, we just simply have that n of L has to be equal to 0. So n of L is equal to 0 is equal to 0. It implies a plus b of times L is equal to 0. So simply b is minus a by L, but a is equal to n, so b is minus n by L. So the equation that we will get for this electron concentration is simply it will simply be, wait a second, n plus minus of n by L x. So it would simply be n times 1 minus x by L when this x lies between where this x lies between 0 to L. So this is the simple equation for the electron concentration that we will be obtaining. Okay, now the total number of electrons that we will be having, we just have to multiply this concentration with the volume. So the total electrons is simply concentration, this electron concentration into the volume. So this simply means this we know that A is the cross sectional area. We have been given this cross sectional area for this material is A. So it would simply be A times integrating this electron density between the limits 0 to L and times 1 minus x by L dx. So it simply is A times n. This integral of 1 is L, so it's x between the limits 0 to L, so it is L. Wait a second. And for x it will be minus x square by 2 L between with upper and lower limits being L and 0 respectively. So it is A n L minus L squared by 2L. This L and this L will go, and we will be left with L minus L by 2. So it will be A and L by 2. So this is the total electrons that are present. Now let us check the options. So the option, I think the option C is the correct option, and the problem has been solved. Now there is another problem. It is also related to some semiconductor bar, which is here it has been told that the semiconductor is p doped with acceptor concentration being 10 to the power of 70. So we have been given these diffusion constants for these electrons and for these holes as well, and we have been given these the times as well for tau n naught and the tau p naught, and we have been given the generation rates as well, and the generation rate is given to be equal to 10 to the power of 20. We have been told that this semiconductor bar is previously under the equilibrium for some what we can say some time less than t equal to 0. This is held under the equilibrium, and after that time at t equal to 0, we are using some external source to generate the excess carriers at some rate which is given 10 to the power of 20 centimeter cube per second, and this source is then turned off after some time, and we have been told to find the excess electron concentration at time t. So first of all, we should be aware that since this is a p-type material, the minority carriers will be electrons. So let me write it down first, because it is a p-type material, the minority carriers are electrons. Now if we use the continuity equation, we can simply say this minority electron concentration is given by This Dn is the diffusion coefficient, which tells us the how easily they can move under these excess carriers can move under the influence of this concentration gradient. Mu n is the mobility, and it tells us how the electrons will move under the application of drift field, that is some external drift due to some external electric field which generates some force on the electrons, as a result of which they drift. So GL is the generation minus delta n by tau n naught is equal to d by delta n by d tau. Now these two terms will simply cancel out. This will be equal to 0, this will be equal to 0. Reason being that this is uniform generation, and we have no electric field, no electric field, no electric field, and this is uniform generation. Okay, so now we will be just left with these terms, that is GL. Thus we will be left with GL minus delta n by tau n naught equal to delta of dn by dt. Okay, now as we have seen it in our mathematical courses, this is just the linear differential equation. Okay, so this is linear differential equation. We need to solve this. So let us take this. Let's represent this in more familiar form, which is this d by dn of dt plus delta n by tau n naught is equal to gl. Let me put it in some form, some common form that we know, common form, that is dy by dx plus py equal to q. So here uh, p is 1 by tau n naught, q is gl. Okay, so the integral of p dt is simply integral of 1 by tau n naught, which is simply t by tau n naught. Okay, now the integrating factor, this integrating factor if is simply exponential of integral of this p dt. Okay, okay, yes, this is correct. So the integral of p dt is simply e to the power now t by tau n naught. This is our integrating factor. Simply the solution for this is y times integrating factor. Wait a second. Oh, sorry, I had some call to attend. So this y times the integrating factor is simply the solution equal to is the solution with the integrating factor multiplied by the q and integrating over dx. So our solution will simply be delta n. Integrating factor in our case is tau by tau n naught, and q in our case was simply gl, I guess. Yes, it was gl. So it is q is gl, and integrating factor is simply e to the power t by tau n naught plus some constant c. Now this solution is simply gl uh, by tau n naught plus this exponential of t by tau n naught plus some constant c dash delta n e to the power t by tau n naught. But at t equal to 0 there was no excess carriers. So at t equal to 0 there was no excess carriers. Delta n is equal to 0. So it implies 0 times exponential of 1 is gl tau n naught plus c dash, or simply c dash is equal to minus gl times tau n naught. It implies delta n e to the power of t by tau n naught is simply gl tau n naught e to the power of t by tau n naught minus gl tau n naught. Let's divide by both sides by exponential of t by tau n naught, and we will be left with this thing gl tau n naught. Let's take it as a common 1 minus e to the power minus t by tau n naught. So this is the excess carrier concentration as a function of time that we have got. Now I think we were required to find it at some time. Yes, it is at time t equal to 2 microsecond, and gl is 10 to the power of 20, and t and naught we require this value. It is 1 microsecond. So let me write these values first. So this gl is 10 to the power of 20 centimeter cube per second, and tau and naught is 1 microsecond. So this delta n at t equal to 2 microseconds is simply equal to gl times tau n naught, 10 to the power 20 into 10 to the power of minus 6, 1 minus exponential of minus t by tau naught. T is 2 microseconds and tau n naught is 1 microsecond. So it is simply microsecond will go. It is 10 to the power of 14, 1 minus e to the power of minus 2. So basically let me solve this e to the power of minus 2. Let me solve it on calculator first. E to the power of minus 2 is simply 0.135 minus 1 into 10 to the power of 20. It comes to 14. It comes out to be equal to 8.65 into 10 to the power of 13. Okay. So basically the value for this is 8.65 into 10 to the power of 13. Fine. Okay, this is fine. Now this unit should be per centimeter cube. Okay, yes, that's when it will come out in the values of per centimeter cube. So now we have another problem related to this semiconductor bar, where this semiconductor sample has a cross sectional area of 1 centimeter square and thickness equal to 0.1 centimeter, and we have been told to determine the number of electron hole pairs. We have been told to find the number of electron hole pairs for what we can say. uh, we have been told to find this electron hole pairs concentration when we have been told actually to find this per unit volume per unit time by just simply having this electron and hole pair concentration to be equal to uh, this electron hole pairs basically are being generated by the light absorption. So we have this a uniform absorption of some 1 watt power which is at some wavelength, which is given to be equal to 6300 angstroms, and we have been told to assume that each photon creates one electron hole pair. So basically we have been told to find this what you can say the number of electron hole pairs that are being generated due to this absorption that is occurring. So one condition over here is that this the each photon this each photon, the light that is being illuminated, each photon creates one electron hole pair. So it implies, so what does it imply? It implies that number of electron hole pairs generated is equal to number of photons. Okay, so this is the number of electron hole pairs that are generated is equal to number of photons. Now the power is 1 watt and the wavelength is 6300 angstrom, but this energy of one photon, we can use our famous relation which relates the energy with the frequency. Energy of energy of one photon is simply h nu. We have been given the wavelength, so we will replace nu by c by lambda, which is now the Planck's constant 6.626 into 10 raised power of minus 34 into 3 into 10 raised power of 8 divided by the wavelength. Remember, this is in angstroms. It is 6300 angstrom, which is 6300 into 10 raised power of minus 10, or simply 6.3 into 10 raised power of minus 7. So let me solve this simply. So it is simply 6.626 into 3 divided by 6.3. So it's 3.15, and 3.15 and above, if we take this 7 above, it will be 15, it will be 19. Simply it will be 10 to the power of minus 19 joule. So this is the energy of one photon. But we have been given that this energy applied per second is 1 joule, and power is the energy per second. So let me write it like this: energy applied per second is 1 joule. Power is energy per second. Okay, so the number of what we can say, number of photons generated will simply be number of photons generated per second is simply the 1 joule divided by 3.15 into 10 raised power minus 19. That is the energy of one photon. Energy of one photon has to be divided with the total energy. So it is simply 1 divided by 3.15. So let me check. So 1 divided by 3.15 is 3.17. It is 3.17 into 10 raised power of 18 photons per second. Okay. Now this question, I guess, says that we have to do it per unit volume as well. So the number of electron hole pairs generated per second per unit volume is simply equal to 3.17 divided into 10 raised power 18 divided by volume. Volume is simply, I guess, it is 1 centimeter. It is 1 centimeter square into 0.1, so it is 0.1 centimeter cube. So it is simply 3.17 into 10 raised power of 18 0.1 centimeter cube. It is 10 to the power of minus 1, or simply it is 3.17 into 10 raised power 19 electron hole pairs per second per centimeter cube. Okay, so the value is 3.17. Option A is matching our values, so we will go with 3.17 value. Now this problem is also on this sixth problem. This is also on this single semiconductor bar, where this semiconductor bar silicon it has been doped with donor this time, and the donor impurity concentration is the 10 to the power of 16 per centimeter cube. And to this material we are using some external light source to eliminate this material, as a result of which we are having excess electron and hole concentrations that are being generated. Now there is one condition over here, that we have to assume that each photon generates one electron hole pair here also, and under this elimination we have to find the location of the Fermi levels in this semiconductor with respect to the intrinsic Fermi level. So basically initially when the material was doped, it was in equilibrium, thermal equilibrium, but due to this illumination, due to this light, shining of the light, we will be having this excess carrier generation, as a result of which the material will move out of the equilibrium. So as a result of this, we will be having a different Fermi levels that we will be requiring in order to uh, represent the electronic and whole levels inside the semiconductor material. So basically, this will move, or this light illumination will move the material out of the equilibrium, and we will be having some Fermi levels, which we will be calling by the name of the quasi Fermi levels, and those quasi Fermi levels will be we will see whether they will be different for both the electron and holes, or whether they will be same for both of them. So they basically, the the system the system the semiconductor system moves away from thermal equilibrium. Okay. So the let's see the this majority carrier concentration first, since this is an N type, as we have used donor impurities. So majority carrier concentration is simply equal to the N naught, which is simply equal to Nd, approximately equal to 10 to the power of 16 centimeter cube. So it simply means that the minority carrier concentration is equal to P naught is equal to Ni square by Nd. Ni is, it is 10 to the power of 10, this is 10 to the power of 10, so it is 10 to the power of 10 whole square by 10 to the power of 16, which is simply 10 to the power of 4 per centimeter cube. Okay, so the let's first look at the Fermi level positions when we were in thermal equilibrium. That when we were in thermal equilibrium, the Fermi positions were as under. So let us solve the for the Fermi positions, so that we can get some insights into the what happens when we eliminate the material with some external source. So this is simply uh, the EFN, okay, minus EI is simply given by KT ln of N naught by Ni. Okay, so basically this is, wait a second, what has happened? Oh, wait a second. Yes. So EFN minus EI is simply KT ln of N naught by Ni. So we know the KT is the thermal voltage, and we have been given this value to be equal to 26. You can see it over here, 26 millivolts. So it is 0. Wait a second. So it is 0.026 ln of N naught is 10 to the power of 16 divided by 10 to the power of 10. So it simply means that this is 0.026 into ln of 10 to the power of 6. So let us do the ln of 10 to the power of 6, which is 13.8 into 0.026. So it comes out to be approximately equal to 0.36 electron volts. So this is the band gap. Sorry, it's not the band gap. This is the difference between the electronic Fermi level and the intrinsic level. So now for the holes, it is simply EI minus EFP equal to KT ln of P naught by Ni. It is simply 0.026 ln of P naught is 10 to the power of 4, Ni is 10 to the power of 10, so it is 10 to the power of minus 6 simply. So it will be just the opposite of this, opposite sign. I would say the value would be same, magnitude would be same, but the value will be different. So value will be opposite to its sign. So it is minus 0.036. So the Fermi level is 0.36 above the intrinsic energy level. So this is simple. Now, since we have illuminated the light, we have used some external source. As a result of this thing, we have this electron hole pair generation, and this is 10 to the power of 12 photons are irradiated on the material, and each photon generates one electron hole pair. So let us say that this since a light illumination creates 10 to the power of 12 per centimeter cube electron hole pairs. I guess it's per second. Yes, electron hole pairs per second. So we have to now assume that the steady state has been reached, and now the excess electron and hole concentrations is delta n and delta p, and it is 10 to the power of 12 per centimeter cube. So we have assumed that each electron hole pair, the light illumination creates one electron and one hole pair. So now the electronic concentration would simply be equal to n naught plus this excess concentration, which is simply 10 to the power of 16 plus 10 to the power of 12, which is approximately equal to 10 to the power of 16 per centimeter cube. Now for the holes, it is P naught plus delta P, so it is 10 to the power of 4 plus 10 to the power of 12, so it would be approximately equal to 10 to the power of 12. So what have we seen over here is that the minority carrier concentration was significantly affected by the since these holes were the minority carriers in this n-type material, it was significantly impacted by the semiconductor when this semiconductor was illuminated by external light source, as a result of which we had this generation of electrons and hole pairs, and this resulted in the uh, drastic change to the concentration of the holes. So the now this position of Fermi levels after elimination is simply now EFN minus EFI or EI KT ln of N naught. Now this is not N naught, this is N, which is actually equal to N naught simply, approximately. It is N by Ni, it is 0.026 ln of 10 to the power of 16 by 10 to the power of 10, which was the value we got previously. This is 0.36. So it is approximately simply equal to 0.36. Now for holes, it is EI minus EFP is equal to KT ln of P by sorry P by Ni. So the value of P is now 10 to the power of 12. So it is ln of 10 to the power of 12 by ln of 10, and it is simply ln of 2. Let us check the value of ln of 2. Wait a second. Ln of 10 to the power of 2 into 0.026, it is 0.12 approximately. It is 0.12 electron volts. So we have now different electron and hole Fermi levels. So this different uh, Fermi levels to capture the non-equilibrium situation, not to capture this non-equilibrium situation. Okay, so we have got different Fermi level for these holes, and since the electronic concentration was not significantly impacted, as a result of which this is approximately equal to 0.36 electron volts. Now let us check the options which are matching to our values. So clearly option B is matching, so we would select this 0.36, since this 0.36 remains for the electrons, and for holes the Fermi level is now 0.12 above this this above this what we can say below this uh, intrinsic level. For this what we can say electrons, it is 0.36 above the intrinsic level, and for holes it is now 0.12 electron volt below the intrinsic level. Now there is another problem, similar kind of a problem that we have been seeing uh, for the semiconductor bars that we are studying, and this time it says that this intrinsic silicon wafer is now doped with the arsenic impurity. So this arsenic will act as donor impurities, as a result of which the material will be n-type. So it has been told that if a small amplitude low frequency voltages of some magnitude V in is applied across the semiconductor block, the current flows through this, and the current is some denoted by some I in. Now we have to assume this block is some cube of side 10 micrometer, and this we have to also assume the complete ionization has occurred for the donor atoms, as a result of which we will be having uh, this 10 to the power of 16 uh, electronic concentration in the material. So we have been told to find the dynamic resistance. Clearly this dvi in by di in is the this dynamic resistance, and the intrinsic carrier concentration is being given has been given to be equal to 10 to the power of 10, and electron mobility is simply 1000 centimeter square per volt second. Now let us see the how we should solve this problem. The problem simply states that this ND is approximately equal to N naught is equal to I rather using N naught I will use N. N is equal to 10 to the power of 16 per centimeter cube. Okay. Now the whole concentration will simply be equal to Ni square by N. So it is, we have used the law of mass action. So this is simply equal to 10 to the power of 10 whole square divided by 10 to the power of 16. It is 10 to the power of 4 per centimeter cube. Okay. This dVn by dy
I in is dynamic resistance. So uh, it is simply given by rho L by A. So it is rho L. Since this is a cube, area will be L square. Simply it will be L square. L and L will go, and we will be rho by L. Okay, but rho is simply 1 by q times n times mu n plus whole concentration times the whole mobility. But since these holes are minority carriers, p will be very less. It is 10 to the power of 4 as compared to the 10 to the power of 16. So we can approximately say that this expression reduced to q times n mu n. So if as n is greater than much greater than p, so this simply means that this value dV in by di in is equal to 1 by q n mu n times L. So it is simply q is 1.6 into 10 raised power of minus 19, n is 10 to the power of 16, mu n I guess was 1000. Yes, it is 10 to the power of 3, and L is where is L? 10 to the power of uh, minus 6 micrometer, but we have to convert it into centimeter. So it is 10 to the power of minus 3 centimeters simply. Now if I solve for this, so this will go with this is 10 to the power of minus 3, it would become 10 to the power of 3, 1 divided by 1.6, 1 divided by 1.6 is 0.625, so it is 0.625 into 10 raised power 3 ohms. Now let's check the options. Answer is in kilo ohms, so it is 0.625 kilo ohms. Okay, okay, I guess 0.625, there is no option that is matching, so we will select option E, which is none of these. Now moving towards another problem from this the yesterday's session that we had, but since I was not able to record yesterday's session, so there was some problem with this my OBS studio, so I actually was not able to record. So I am again you teaching the same problems that we discussed in the yesterday's lecture, and we also had some good discussions, but sorry for that we will be missing those discussions since I had not recorded the session, yesterday's session. But to have some what we can say, to allow other people who didn't join the yesterday's session, to allow them to check the solutions that we had some posed yesterday, that we had solved yesterday, the questions we had solved yesterday. I am again recording the same session without the students. So now this same problem that we yesterday studied, and on this problem we had spent quite a lot of time while discussing how these traps help us in the this recombination and generation mechanism, how they help us to what we can say, they act as an intermediate state to help us, for example, move from, let's say, from first floor to the second floor, or from second floor to the first floor, by providing us alternate, for example, or not alternate, by providing us steps to move in what we can say, in small increments or small decrements. So these steps, like these staircases, you can consider these traps those staircase. For example, a staircase lying in the middle, that is middle, sorry, I shouldn't say middle, a staircase lying inside this band gap of the material, that is trying to act or trying to influence the recombination and generation mechanisms by providing these electron and holes. They alternate, or they easier way for the mechanisms of generation and recombinations. Now this problem says that we have to find the location of traps inside the band gap, that produces this thing, this the most efficient trap assisted recombination. And this there is some condition on the minority carrier lifetimes as well. It has been told that these minority carrier lifetimes for both electron and holes are equal. Okay, so we have been told that the minority carrier lifetimes for both electrons and holes is equal. Wait a second, let me put the laptop again on charge so that we don't run out of the gas. Wait a second. So now the we have seen in the lectures, as professor told, that he stud in steady state, this recombination, the recombination rate is given by simply r n p minus ni square n plus n1 tau p is the minority carrier lifetime of whole, p plus p1 into tau n. Now this n1 is simply equal to ni times gt. Gt is the degeneracy factor of the trap, exponential of et. Et is the trap level, ei is the intrinsic level, by kt. And simply p1 is ni by gt exponential of ei minus et by kt. Now we have to find the maximize this efficiency of this trap assisted recombination. So in order to do that, we need to find the location of the trap level. So what we will do, we will simply derivate this recombination rate by the by this trap level in order to get its position in for the maximum condition. So it would simply mean I would put dr by det to be equal to 0. Now if I do the derivative for this equation, derivating this equation dr by det, I have just these n1 and p1, which are the functions of the what I can say, what these are the functions of the this trap level. Rest are independent of the trap energy level. So if I try to derivate this thing, it would simply be np minus ni square minus 1 divided by this thing n plus n1 tau p plus p1 tau n whole square times the derivative of this thing, which is tau p dn1 by det plus tau n dp1 by det. So if I now put this equation to be equal to 0, it simply would mean either this np minus ni square has to be equal to 0, but this is not possible because it is not in equilibrium. So np is not equal to ni square because we are in non-equilibrium situation. So the only thing that is left over here is this thing now. This thing tau p dn1 by det, this tau p dn1 by det plus tau n dp1 by det. This has to be equal to 0. Now if I derivate this tn1 by det, so it would simply mean dn1 by det would simply mean ni times gt. This has to be divided by kt, so it is ni gt by kt exponential of et minus ei by kt. So this whole thing is simply equal to n1, so it is n1 by kt. For dp1 by det, it is simply this thing, this ni by kt gt will come, so it would be ni by gt, rather I should say kt gt exponential of et minus ei by kt. Okay, so it would be like this, it would be p1 by kt. Okay, since it is minus, it should be minus 1 by kt. Okay, yes, so it should be minus 1 by kt. Okay, minus 1 by kt, so it is minus p1 by kt. Now let's put these values in equation a. Put in equation a, so I would simply have this value tau p n1 by kt minus times p1 by kt tau n equal to 0. So this kt and kt will go, okay, and we will be left with n1 by p1 is equal to tau n by tau p. Now if I substitute the values of n1 and p1, n1 is simply equal to ni gt exponential of et minus ei by kt, and this thing p1 is simply equal to ni by gt, it is equal to ni by gt exponential of ei minus et by kt is equal to tau n by tau p. Now this ni and ni will go, it would become gt squared exponential of et would go upside, et minus 2ei by kt is equal to tau n by tau p. But I think we had been given this degeneracy value, this degeneracy gt, but gt is equal to 1, and let's take ln on both sides. It is now ln of tau n by tau p is equal to 2 times et minus ei by kt, or simply et is equal to ei plus kt by 2 ln of tau n by tau p. uh, we have been given some condition for these minority carrier lifetimes of these holes and the electrons as well, and it was that tau n is equal to tau p. So it implies this et is equal to ei, and ei lies approximately, not exactly in the middle of band gap, near the middle of band gap. So near middle of band gap, near. Okay, so let's check the options. Option A is very close to conduction band, which is false. Option B is very near to the middle of band gap. This is correct option. Okay, now let's move towards another problem, which is actually on this problem also we had some discussion yesterday, that when we were saying that how to approach these kind of problems, and one of the students yesterday, he came up with him and with this Einstein's equation, and he said that I have just seen that this equation here deals with the diffusion length, so we will be requiring this diffusion constant. So we were spot on when we were saying that we need to have this diffusion length, and for that we will be requiring diffusion constant, and for the diffusion constant we will be requiring to have the what we can say, this uh, Einstein's relation. So let's solve this problem again today. So this is the minority carrier lifetime of electrons. Tau n is equal to 9 into 10 to the power of minus 12 seconds, and mobility of electrons is simply 350 centimeter square per volt second. In here the thermal voltage is 25 millivolts. 25 millivolts. Now, if we will be using this Einstein's relationship, which says that the diffusion constant by this mobility is simply kT by Q, or simply this is equal to Vt. Okay, so this diffusion length is simply equal to this diffusion length is simply equal to the diffusion constant times the diffusion time under the square root. So now this dn is simply mu n times vt, so it is mu n times vt tau n. Okay, so it is mobility is 350 centimeter square per volt second, Vt is 25 millivolts, and tau n is 10 to the power of 9 into 10 to the power of minus 12. So let's solve for this. So let's solve for this. It is simply 350 into 25 into 9, 78750. It is simply coming out to be equal to 88.7 into 10 raised power of minus 7 centimeter, or otherwise, other way we can say that since it is 10 to the power of minus 6, it is 8.87 into 10 raised power of minus 6 centimeter. So it's 8.87 approximately, and option A is the closest that we should select, since it is approximately equal to 8.9. Now let's move towards another problem. Uh, this problem is also quite interesting, and it is actually, it gives us a sense about how this conduction band bending, or the valence band bending, gives us insight into the, what I can say, insight into the electric field, how this electric field, how this slope of this conduction band is related to the electric field. We have already seen this thing, that there is a relationship between the slope of the conduction band and the electric field. So now, in this problem, we have been given some concentration as a function of x, and we have been told to find the electron current density. So electron current density will basically be sum of two and current densities. One will be the drift current density, and the other will be the diffusion current density. So if I write down the full expression for this thing, so this is the J total, which is the total current density, is simply equal to J drift plus J diffusion. Okay, so drift current is simply given by Q, electronic charge times mobility into electron concentration times the field, plus this diffusion is simply given by electronic charge times the diffusion constant multiplied by the concentration gradient. Now this concentration was simply equal to n of x is equal to 10 to the power 15 exponential of q zx by kt. Okay, now this j total is simply equal to q times mu n times n, and the electric field is simply minus zero point 0.1 volt per centimeter. So it is minus 0.1 volt per centimeter. So this q times dn by dx would simply mean this expression is simply q by kt times z into 10 to the power of 15 exponential of qzx by kt. Okay, so yes, so this thing over here is itself equal to n, and this expression will reduce to q mu n times n into minus 0.1 plus q dn q z by kt into n. This value of z has been given to be equal to 0.1 volts per centimeter. So it would simply mean this thing is qn. Taking this qn common, this qn as common, I will be left with mu n minus 0.1 plus dn q by kt 0.1. Okay, this is the value I will be left with, this equation I will be left with now. And now let me add some slide again, and use the Einstein's relation. This dN by mu n is kT by q, or simply dN q times q by kT. Sorry. Oh yes. Uh, q by yes q by kT. Uh, am I correct? Yes. Q by kT is equal to mu n. Okay. So this thing over here is equal to mu n. So it is simply this J total is simply equal to Q times n minus 0.1 mu n plus zero point 0.1 times mu n. So simply this J total is equal to 0. So we will be getting this to be equal to 0 ampere per centimeter square. Now let's check the options for this. Okay, there is no option. Oh yes, none of these. We have this option D, which is matching. So we will select this option, that is none of the above. So none of the options that was given was matching. So we have gone with the none of these options. Now this problem, as we had discussed in the live session, that we had vastly discussed this metal semiconductor junction, and we had studied how this can result in two type of contacts. One is the Schottky contact and other is the ohmic contact. And this Schottky contact, this will offer some resistance to the carriers that are trying to that are trying to move within this metal semiconductor at this metal semiconductor junction, and how this ohmic contact will allow the carriers to move freely from the metal to semiconductor or semiconductor to metal. So these two type of contacts that we had seen, that these both depended on the metal work functions and the electronic what we can say electronic semiconductor wave functions. And we have seen that the semiconductor wave function was a function of doping. However, the electron affinity of the semiconductor was a fixed quantity. So this chi s was fixed for a particular what we can say, for a particular semiconductor. However, for a metal, we had drawn something like this. If this is the vacuum level, then this will be the Fermi level for metal. This will be the metal work function, and this is fixed. For the semiconductor, we had drawn something like this. This is the vacuum level, and this is the, for example, conduction band edge. So this difference between these two is given by this value. Let me write this q times phi m. So this is q times chi s. This is the electron affinity, and this is a fixed for a semiconductor material. How it would change with different materials. However, for a particular semiconductor, it would be fixed for a particular semiconductor. If we are not sort of stressing or straining it, we are not changing its let's constant. So these things, these chi s, they will remain same for a particular material, unless we are not subjecting it to some strain or stress conditions, or we are not changing its let's constants. For example, there will be let's mismatching at the, for example, interfaces that might lead to this expansion of the material at the edge, or at the interfaces, as a result of which there might be a change. Otherwise, if we have just this semiconductor bar, which is in its pristine form, this chi s should remain same. But we had said that this we can say this if this is the intrinsic level, and this is the this is the valence band edge, and we had said that this is the semiconductor work function, and this semiconductor work function will change with doping, let's say. Change, it varies, okay, it varies. So when drawing the Schottky metal contact, we had clearly seen yesterday that we actually I have told you people to as an home assignment to draw these metal semiconductor contacts for different conditions. Like for example, we have metal work function greater than the semiconductor work function, considering the material is n type. Other case would be the metal work function is less than the semiconductor work function and the material is n type in that case also. And for the p type, similarly, we will have this the metal work function is greater and the metal work function is less. So for all those four cases, I want you people to draw the energy band diagrams by yourself, so that you get some useful insights, or what we can say, some these insights will provide you the will lead you, will provide you the path that will help you to draw the energy band diagrams for the rest of the course, for the MOSFETs, for the PN junctions, for the hetero PN junctions. You will also be able to understand the physics to a large extent if you are able to draw these energy band diagrams by yourselves. Just remember the charge transfer rule, and the Fermi levels will be aligned in thermal equilibrium. The Fermi level has to be continuous across the both the materials when we are considering it in thermal equilibrium. So considering that fact, we join the two Fermi levels, we do the charge transfer, and we see how the region at the interface, whether it has depleted on the this semiconductor side, or whether it has resulted in the accumulation and the of the, for example, the electrons in the uh, n side of the semiconductor. So we will be having this Schottky or ohmic contact accordingly, depending whether this whether what was the condition on the metal work function and the semiconductor work function, and what was the conditions on the for example, the doping levels as well. So it would try to influence the slope of this thing, this conduction band edge near the interface. That more, if we are trying to dope the material more, the edge will be sharper as a result of the let me draw this first. This for example, for this case, this phi m greater than phi s. Let me draw the energy band diagram. For example, if I am having this as EFM, I will be having something like this. This is EC. At the far from the interface, everything remains the same. Okay, so we have to not worry for at far from the interface. This is EV. This was EF. Okay, the EFM and EFS are same. Now this triangular barrier, what you are seeing over here, this changes with the doping. So if we dope the material more, this will just shrink and then continue to shrink, as a result of which there will be tunneling of the carrier. So this will result in the more densely doped the semiconductor is, the more steeper this slope of this mm, triangle will be, as a result of which the tunneling will be more. So this barrier over here, this barrier over here is the Schottky barrier, and this barrier is, if I draw the vacuum level. So this is simply the Q phi m, this is Q phi s. So this barrier is simply this Q phi b is simply equal to Q phi m minus Q phi s. So sorry, not Q phi s. Actually, this is chi that I have drawn over here. Q chi s. So this is Q chi s. So since this is material dependent thing, and this is also material dependent thing phi m, so both phi m and chi s, the electron affinity and the metal work function, does not depend does not depend on doping. Sorry, what has happened? Does not depend on doping phi m and chi s. So this phi b, which is the Schottky barrier, so it does not its height does not depend on this. Its height does not depend on the doping, although the doping will change its what we can say thickness. The thickness will be changed by the doping, but the height will remain the same. So as a result of the increase in doping, we will be having thinner this triangular barrier, as a result of which we will be more tunneling of the carriers. So this is as simple as that. Now for this question, it says that how does the Schottky barrier height vary if the doping in the semiconductor decreases. So it is simple. The answer to this question is simply that it remains unchanged. So it remains unchanged. So I guess since this is the recording of the same lecture that I delivered yesterday, and we had some good discussions yesterday as well, and this is just the repetition of the problems that I solved yesterday, but I was told to do it again since I had missed the recording. So I am just trying to solve the problems that I had solved yesterday, and this problem was the last problem that we had discussed. And in the yesterday's live session, I had told you at the end to draw the energy band diagrams for all the four cases. In this recorded presentation, I am again saying the same thing, so that you people get useful insights into this thing, into the energy band diagrams, that I want you people to be able to draw the energy band diagrams easily after the course ends, so that you you must have heard that all the semiconductor device physics happens at the interface. And all the if a person is not able to draw this energy band diagram for a particular material, or for a particular, or we can say for particular heterostructure, or for a particular junction, then he should consider that he does not know the physics of the material. So if you are smart enough, you should be able to draw the energy band diagrams. You should be able to learn how to draw the energy band diagrams, and how to interpret the energy band diagrams, in order to get major insights into the physics of the materials that we are studying. So I guess this is it from this recorded session. I had missed this recording. I was not able to record it yesterday, so I am recording it again. So thank you if you listen to this PPT. Thank you again. So let's end the session.